Okay, thank you. I'm a PhD student at the University of Brescia, as Ian said, and I'm under the guidance of Professor Antonio Visioli, and I'm collaborating with Professor José Luis Guzmán from the University of Almeria, where my physical project is located. The outline of this presentation is the second, so I will give a brief introduction about the situation where my project is located. Then I will describe the microalgae as a solution, and finally I will deliver my research activities such as objectives, current state of the work, and future work. So the last few decades has come along with faster population growth, intensive urbanization, and a significant increase in the use of fossil fuels. These aspects have brought a great advance in the quality of life, such as the availability of electricity in every home, but also major problems that society must address as soon as possible. These include mainly water pollution due to population growth, air pollution due to increased industrialization, and finally, climate change. Microalgae is a solution that can tackle both of the problem, so water pollution and air pollution, because they have the possibility, they are microorganisms that they have the possibility to grow and absorb the nutrients, which are nitrogen, phosphorus, and carbon, that in our case, nitrogen and phosphorus are also the main substances present in wastewater. Instead, carbon can be taken from the carbon dioxide, which is the main character of the global warming. They need also energy for growth, and they use the solar energy since they are photosynthetic organisms. They have two main products of this process, which are the purified water and the biomass. The biomass can order further use in pharmaceutic, biofuel, fertilizer, or even food for animals or human. Some study show that the microalgae has an efficiency of purified water between 60 and 90%, and also they can fix up to 1.83 kilogram of CO2 per kilogram of biomass, so making them a suitable solution. In general, the microalgae to grow needs bioreactors, and as shown in the literature, they can be divided in two main families: closed and open pond. The main difference between closed and open ponds are the fact that in the closed one, there is a physical barrier between the environment and the microalgae. And instead, in the open one, there is no barrier. The closed tubular bioreactor are shown in the figure, are usually composed of interconnected pipes where the fluid and the microalgae flow and take place the biomass production. Usually they are used in order to produce substances that are needed for pharmaceutic user, and where there is the need to avoid the external agent contamination. Instead, in the open pond are just a pool filled with water and microalgae, and let them circulate inside the pool. And in this case, they can be used, for example, for wastewater treatment or biofuel production, or even fertilizer production. In this case, there is no the need of avoiding contamination. There is also a final aspect to take into account, which is the cost of the two solutions. The first one has a high maintenance cost. Instead, the second one is very cheap. In our case, we decided to use a raceway bioreactor, which is an open pond bioreactor, because we want to address the wastewater treatment and the biofuel production. And in this scheme is shown how a raceway bioreactor is composed. So on the left, we have the wastewater, CO2, and air, which are the income inside the bioreactor. And the wastewater and the CO2 supply the nutrients for the microalgae. Instead, air is used in order to decrease the oxygen level inside the medium, due to the photosynthesis process of the microalgae that produce oxygen. Then on the top, we have the environmental agents. Since it's an open pond, we have, for example, the sunlight, the rain, or even external microorganisms. In the right, we have the outcome of this process, which are biomass and purified water. And in the bottom, we have the four main variables usually measured in a raceway bioreactor, which are pH, dissolved oxygen, concentration of biomass, and temperature. These four variables are the main variables that influence the biomass production. In the literature, we see that there are modeling techniques, and they can be divided in two main families: the first principle model and the data-driven model. The first principle model are models that are built upon theoretical knowledge, such as chemical or physical in our case, and usually they show a high number of parameters, and that can be a problem due to the fact that they require a huge amount of informative data. But they shown at the end a high accuracy in the description of the system. Instead, data-driven models are usually just taken from the data, and they usually have a low number of parameters, require not a huge amount of data. But they, at the end, represent just a low accuracy and just a local expression of this model. From a control point of view, the first principle model are used usually for high-level control purposes and for describing the system for a long time. Instead, the data-driven model are usually used for a low-level control where just a local description of the model is enough. In the control part, we can also divide them in two groups, which are related to the groups seen before for the modeling, because they are related to each other. In the low level, so we have the low level and the high level. In the low level, we can individuate three main control loops, which are pH, which is mainly controlled by CO2, dissolved oxygen, which is controlled by air, and temperature, which can be controlled by a heater, so they heat. Obviously, they are correlated to each other, but these are the main control variable that we have to control them. And instead, in the high-level part, we have the biomass production in order to be maximized. Because if we maximize the biomass production, we will have also the maximization of the water purification and CO2 fixation. The objective of our work is to maximize the biomass production. And so in order to do that, we have to start from the low-level control, so controlling the pH and the dissolved oxygen. Then we can move to the hierarchical optimization that take into account the maximization of the biomass production. But in our case, we are working with industrial scale bioreactor. And so we have also to take into account the economic part of this system, because the biomass produced can be sold, and also the system itself has some cost of maintenance. And so we have to find a trade-off between the cost and the economic benefit of the biomass production. We firstly start to identify the model in order to obtain a model to control the system. And so we define a new experiment design model that take three main concepts into account: persistent excitation, maximization of the operating point because the system is nonlinear, and constraint ensuring because our system has to work, for example, for the pH in a certain limit. For example, in this case of the strain that we are using is between 7 and 9. And so we have to ensure it. Furthermore, we are working on a block-oriented model predictive control, which is using a block-oriented model in order to describe the system in a local area, because we are on the low-level part, and we are using more precisely a Wiener model, which has a linear dynamic and non-linear static. And so we are controlling the pH and the dissolved oxygen with CO2 and air. Our future work is to consider the nonlinearity as a linear time variant model and to develop an adaptive model predictive control in order to adapt the model through time. Thank you for your attention.